My name is Charles Fan, and I'm co-founder, CEO of MemVerge. It's my pleasure to be here. Certainly great to meet all the panelists. Thank you for Stephen's invitation. Tech Field Day has been one of my favorite streaming services, and I learned many new technologies first through Tech Field Day. So it's great for us to spend the next 2 hours here to introduce ourselves to you. We did do a 1-hour session at AI Field Day, but today I think we're going to go into more depth and looking forward to all the interactions with the delegates. All right, so let me first introduce the presenters. We're going to have 3 people presenting. I will start with an overview of the company and the overview of the big memory, which is a new category of product and technology that we're introducing. Before starting MemVerge together with Yue and Shuki, another co-founder, about 3.5 years ago, I was working at VMware for 7 years, leading the storage business unit. And my team developed the product called vSAN, which some of you might be very familiar with. Yue was my co-founder. He's a CTO, and he will come after me and kind of lifting the hood to take a look at the inside of our technology, the architecture, and some of the use cases that we are working with customers on. So Yue is really going to be the stake of this presentation. That's going to go into the technology details. And then Charlie is our director of SE. And he's going to do some demos. So we'll see how much time we can leave for him. And he's going to show you real product. It's live demo, real product work. So you get a more direct sense how the product works. And before this, Charlie was the first SE at Pure Storage. And before that, he worked at a number of companies, including Google, Citigroup, and Merrill Lynch. So this is a lineup for the next couple of hours. As usual, in the Tech Field Day spirit, feel free to interrupt you and Charlie anytime with your questions. We love interactions and to even digress a bit, following your questions, even away from the content we prepared. Let me first introducing the company. So 4 years ago, Shuki, Yue and myself kind of came together. We knew each other for a long time. Shuki was my PhD advisor at Caltech, and Shuki and I started some companies before as well. And so we've been in touch. He's been my mentor, my friend, and my colleague for 25 years. And we've been talking to see what's happening in the infrastructure space. Like our experience have been developing system-level software, building infrastructure for enterprises. And Shuki was a co-founder of Extreme.io and of Infinity before this. And so we have to form our vision, our thesis of what the future holds. And when we look at the future of infrastructure, future of the enterprise data center, we see 3 keywords that's going to happen. The first one is multi-cloud. There is no denying that the trend to move to cloud is strong and present. In particular, the leading public cloud are becoming the most important infrastructure providers to the enterprises. The on-prem data center will remain, but overall the percentage will be shifting more and more towards public cloud. And these public clouds will be like supercomputers, and there will be a few of them in the world. There are like 3 in the US, like 2 in China, and there are like a few others around the world. And the workload is going to be spread among them. And there's some stuff that might be still left on the on-prem data centers. But there will be a key: how do you develop and deploy applications in this new world that you have these clouds and then you want to work seamlessly among them. So there's no denying that we're going to be living in a world of multi-cloud. The second keyword that we convince ourselves, we believe the future of infrastructure will become more memory-centric. And this is what we're going to dive into. The reason for this is because of data. Because the data is growing both in capacity and in velocity. That we believe that the storage that we know yearly for so many years will be too slow for the real-time applications that's going to grow more and more. We believe more and more applications will be living in memory, and therefore the infrastructure will need to become more memory-centric. So that's the second keyword that we identified. The third keyword is that we believe it's going to be software composed. And what do we mean by that is, coming from VMware, working there for a long time, we all are imagining and building a world that's more software defined, whether you're talking about compute, talking about storage, talking about networking, and in this case, talking about memory, it's going to be more and more defined by software, which is a more flexible and dynamic way of supplying resources to the application. But we also believe it's going to become more composable. It's because of the heterogeneity of the various devices. Whether you're talking about compute, there are going to be more kinds of computing devices, computing units that's going to be there in the infrastructure. CPUs, GPUs, different AI chips, different FPGAs, etc. The memory side will become more heterogeneous as well. That we have been working with DRAM, and as we are going to introduce, now there are persistent memory of different kinds that's going to be reaching the market. And how do you deliver these various kind of memories and deliver them in software forms in a composable fashion to the applications will become a key. And so will be the networking resources and storage resources and so on. So those are our thesis, that the future data center will be multi-cloud, will be memory-centric, and will be software composed. And now what do we do as a software vendor? Where do we see the opportunity exist? So for that, let me talk about what we call a great memory storage convergence. And the picture where we are showing is a typical computer. And this is a computer, whether you're talking about the server in the data center, or whether you're talking about a PC, or whether you're talking about the iPhone. Inevitably, they follow this von Neumann computing model, which has been around for 75 years, where you have computing units, and this is where the processing is taking place. And you have the main memory, and that's where the data is being placed while it's being processed. And the primary media for main memory for the last 50 years has been DRAM. And DRAM has been a great media. It serves us well. It is very fast, and it's everywhere. It's dominating whichever device you're looking at. But it does have some limitations. It's kind of reaching the limit of its physics. It really couldn't go much denser in terms of the amount of capacity you can provide on DRAM. The cost actually has been pretty stable over the last 20 years. So while, for example, with NAND flash, 10 years ago, it's probably at least 10 times the price, 20 times the price. And the NAND flash today, with DRAM, go back 10 years, is roughly the same price. So you're not really seeing the dropping of the DRAM price. And it is volatile, meaning if you turn off the power, you lose the data. So that means it's not available media that can save your data and survive the power cycles. So you really couldn't build too much data services on top of it for long-term retention of your data. And for that reason, you need storage there. You need external storage, where today it is a combination of NAND flash and magnetic hard drives that are the primary media for storage. And you have tapes as well. So this is a media where it's much bigger than memory, much cheaper, and it is persistent. It can survive power cycles. It can retain data for a long period of time. But it is slow, and it is not as fast, and you really couldn't, really using it as a active data while the data is being processed. You have the computing, you have the memory, you have the storage. And because you have memory, you have storage, you have two buckets to place the bits. That's where I/O comes in. I/O is really the movement of bits between memory and storage. I is when you move from storage to memory. O is when you move from memory to storage. And I/O tends to be slow. And for many applications, especially data-centric applications, I/O tends to be the bottleneck of those applications, especially as data is growing. So that's a computer. But we are seeing a change. But before we go into that change, let me just introducing more motivations from application front. And this we all know well. On the top left, there are many kinds of data-centric applications, whether you're talking about AI, ML applications, real-time data analytics, trading applications on capital markets, high performance computing applications, virtual machines, 3D animation, you name it. They're dealing with data that are bigger and faster, and they're growing in both of those dimensions at the same time. On the bottom right, there's IDC prediction that in the next 4 years, the real-time data is growing faster than all data, and it's going to go to a quarter of all data by 2024. And they also have a study that by next year, 2021, over 2/3 of all enterprises will have at least one mission-critical applications that are dealing with real-time data. And these are the data you need to process at large quantity and high speed at the same time. So this is demanding really what's beyond this typical computer, this von Neumann model can support. So we are predicting, and especially encouraged by the new hardware media that was becoming available. The reason we started the company in 2017 was not by coincidence. That was the year that Intel shipped a product called Optane SSD. And by the way, we are actually not using that particular product, but the inside of that SSD is no longer NAND flash. It was a new media called 3D XPoint. 3D XPoint is a type of storage class memory or persistent memory that people have been talking about for the last 20 years. But that was the first commercially available general purpose storage class memory on the market. That was shipped in Q2 of 2017. And right after it shipped, you and I, we went to Amazon, we got an SSD, we opened it up, and we closed it down, and we tested it, and it works. And it still works with SSD. It's still talking 4K blocks. It's like a storage device and VME device. But we see the potential of this media. We knew Intel was developing this, starting from 2012, and they advertised it in 2015, and it's been delayed. So people were sort of wondering whether it's going to come out or not. But 2017, it came out in SSD form factor, and then gave us confidence it's going to come out in memory form factor. And with this as memory, we think it's going to change the world. We think it's going to give possibility of something we call big memory, where it is you no longer need to have those two buckets. You no longer need to have memory and storage and this data movement I/O that's between them that's slowing everything down. You have the potential of creating a single tier that's a memory tier or big memory tier. And this is going to be consisting of a heterogeneous mix of memory media. And then we can place the entire application data needs into this infrastructure. So that is the vision we conceived back in 2017. And we went ahead to start a company and start developing the layer of software, which runs on top of this hardware that's going to make this possible. So we are creating this big memory software that's going to deliver a software-defined memory service to the applications that are combining the best of both worlds. It has the performance of DRAM, but at the same time, it has the capacity, have the cost, and have the persistence that was not previously available in memory. And this makes possible for the entire application to live in memory without needing storage ever again. So that's the big memory software that we started creating. So the chart on the right-hand side is another prediction on the hardware market, this new persistent memory. As you see, 2019 really was its first year. It was selling for half a year, and today is this year was the first full year of its selling, but it's being predicted to grow at 248% by IDC year over year to reach $2.6 billion, which is a pretty fast growth for the first few years of its new hardware media. And $2.6 billion is just a small portion of the memory market, which is a $100 billion market. So it has a lot of headroom to further grow. And another analyst from Forbes are predicting that the amount of persistent memory going to exceed the amount of DRAM by 2029. So in the next 8 or 9 years, that we're going to see still a mixture of DRAM and persistent memory, and DRAM is not going away anytime soon. It's still faster than persistent memory, so it's going to stay, but the amount of persistent memory actually going to cross over, be more than DRAM in the next 8 or 9 years. Okay, so that's sort of the vision that we have. And now let me go into the product that we are creating. So it took us a little while. For people who are developing this level, system level software, we know it takes like 4 years to create the first version of it. Essentially, this is a sort of a system level virtualization layer that are managing data at very fast speed, at memory speed, and being able to developing various type of data services on top of the virtualization. We have about 35 engineers, and I think we beat the average by a little bit. We shipped our first version in September, 2 months ago, and September 23rd to be exact. That was the general availability of our version 1.0 of the product we call Memory Machine. And this is the world's first big memory software. And the first benefit of this software is it allows the adoption of obtained persistent memory without changing the application. And we'll go into more details of it. Optane does come up, Intel ships Optane, and it has a couple of different modes where people can use it. But these modes are not perfect. There's a memory mode that simulates DRAM, but it has a number of gaps in terms of capacity, in terms of performance, that is not acceptable for some of the customers. And most importantly, it doesn't have the persistence capability of the memory being exposed in the memory mode. It has the second mode, which is called app direct mode. And that's really the best way of using the memory, exposing all the benefits of the memory, but you have to rewrite your app to use the app direct mode. So what we offer is the third mode. We actually use app direct mode so that we can use all the benefits of the memory, but we provide a DRAM compatible interface plus administrator controlled data services, so that we are both compatible with existing applications without change, and then we add a number of powerful features on top of this memory that the IT organizations and users and application developers can enjoy. So let me go into the product, and I'll describe it at a higher level in terms of the value propositions, top level features and value propositions, and Yue will go into the technology, how we achieved these value propositions. So if we look at the version 1.0 of our product, really there are two major features it does. The first major feature is what we call memory virtualization. And this is essentially virtualizing of the DRAM and persistent memory in a tiered fashion. Very similar, if you're familiar with storage system, you have different tiers, and this is very similar, you have tiers. And by having those tiers, we are having the combination of capacity being available to the applications. So today, with Intel Optane and DRAM, you can have up to 9 terabytes of memory capacity available for a 2-socket server. So we have essentially 9 terabytes available. The cost will be lower because the Optane is roughly half the cost of DRAM per gigabyte. So you get bigger memory for a lower cost. And then we do optimized memory allocation and memory tiering algorithm within our software. And this is software defined, so we can configure DRAM PMAN ratio per process. We create something called memory machine for each of the running process or each of the running applications. You can have different DRAM PMAN ratio to get the best combination of cost and performance. So we can deliver DRAM level performance to the applications so that they can get bigger memory, cheaper memory without losing on performance and without changing applications. So this is a great feature for a number of type of customers to lower the TCO of their environment.
So what you're saying basically is that all of us storage people are looking at Optane and saying it's too damn expensive, when in fact I should be looking at this from the server admin side and the application developer side and saying this is so much cheaper than DRAM.
Exactly. That's a great comment because to be honest, we spent the first year and a half of our company debating whether it is memory or whether it is storage. Right? It's kind of both. But at the end of the day, we decided to focus on memory rather than to build a storage product. I mean, I'm sure there are good storage people who can build good storage product with this, but with us, we decided we want to do memory. We want to focus on big memory so that this lower the cost of memory, increase the capacity of memory, and we can add all these cool stuff, which I'm going to go into, that was not before possible on memory. So this is a new type of memory, but it is memory, it saves you cost, and it does all these other wonderful things for you too.
Very cool stuff.
I'm familiar with DC persistent memory and the memory and app modes. Mm-hmm. This is sort of built on top of that, but with some of the additional features that you're listing here, but it's still based on the same sort of foundation, right?
Yes, we run on top of the app direct mode of Optane. And then we also manage DRAM, we put them together, and so southbound, we are managing these resources. Northbound, we're presenting a DRAM compatible API to the applications so that they do not have to change. And so the first feature is sort of a DRAM compatible memory service. It is a volatile memory service to be compatible with applications. It does not change their assumptions. If your memory suddenly becomes persistent, it's actually not good for the application because the security assumptions are broken and all that stuff. So it is volatile. But then we added the second part, which was the persistence on demand. So it's when you want it to persist. That we can have a GUI, we have a CLI. Charlie will give you a demo of that you can decide to persist your memory state at any time through a mechanism we call zero IO snapshot. So what zero IO snapshot is sort of a bastard child between storage snapshot and sort of the application checkpoint. So what it does is it captures the running state of the application, everything that's in memory, everything that's in the CPU cache, we flush it, we persist it right in place on the persistent memory so that we don't incur IO moving them to storage, and we put it in place. We also learn from the storage snapshot so that you can take this in-memory snapshot repeatedly, and we track only the deltas, the change pages. So it really saves the amount of overhead as you repeatedly taking these persisted snapshots. So this is the first of its kind. Essentially, you can do it in-memory snapshot and leveraging the persistence capability of the underlying Optane and taking, basically taking a snapshot of your application. What this allows you to do is you can roll back your application to any of the previous snapshot. So you basically create a time machine of your application. You can roll back. You can restore after crash, going back to any of the snapshots. And we can create sync clones. So you can have multiple application instances running out of the same physical memory while creating this mapping from a previous snapshot without physically replicating all the memory. So all the magic stuff now suddenly become possible once we have this layer of so software-defined memory, and we add this capability of zero IO in memory snapshot. So this is the second feature that's brand new. That was not before known, and we developed it on top of this memory.
I have a question to this because that sounds really cool. I'm getting all those ideas what could be possible with this. Yeah. Would this also work for in-memory database servers, right? So I would accelerate obtain, have it as memory, and then I could snapshot the tables of my database server and could, because I can write and have a backup pretty much that happens in memory.
Yes. The answer is yes and yes, and I think you can present the next couple of slides for me. Those are exactly the two use cases. And in fact, Yue will, in Yue's section, he will go into some of the specific in-memory databases and to see how we can, those are the low-hanging fruits. You know, I think over time, all applications will become in-memory application, will benefit from this. But in-memory databases is one of the biggest low-hanging fruits that we are working with customers on already. So it's a great comment.
Thanks.
Yeah. So in fact, let me go into that. There's a few examples. So the few value propositions. The first one is that it lowers the memory TCO. You know, as I mentioned, between combination of half price obtain and full price DRAM, depending on the ratio, we're typically seeing 30 to 40% cost saving on memory. And the most wonderful thing is the ratio is adjustable. We can decide how much DRAM to be added to a particular process. And this is what we are working with one of the cloud service providers running on KVM. Our software actually runs underneath the KVM hypervisor. And each of the VM is a process. We can decide to configure how much DRAM to add it to that particular VM. And this is running MySQL and running Sysbench query per second on MySQL. The orange bar is a baseline. Without us, just using DRAM, this is supposedly the fastest you can get because our memory is supposed to be a little slower because obtained a little slower. But because of software optimization, as you can see, as we increase the amount of DRAM, you know, if it's only PMEM, it is slower, about 20-some% slower, which is to be expected. But as we increase the amount of DRAM in the mixture of this hybrid software-defined memory, we actually not only meet, but also beat the pure DRAM performance. This so we cannot, yeah, sorry.
Just a quick question. That sounds a little bit like you're leveraging some of your vSAN experience and the DRAM is sort of a staging space backed by the PMEM?
Yes. So certainly my experience with vSAN helped, but the actual algorithm is a little different. This is memory and not storage, and but it's a similar tiering elevator algorithm between the different tiers, and you measure the temperature of data between them and being smart about the placement and the kind of promotion and demotion of the memory pages. So essentially a lot of tricks, a lot of software optimization happened there. And another reason for this performance is we bypass the memory allocator of the operating system, and we have our own memory allocation that are optimized for some of these data-centric applications, so it has higher performance than what operating system has. For those reasons, makes it possible that we have, if one, you know, for different applications, a different ratio that give you the optimal performance for that application. So this is just one example of that. So essentially if I'm a cloud service provider, you can see now I can suddenly lower the cost of my memory without sacrificing anything. So it's like a no-brainer for me to adopt this. Okay, so that's the first one, which is we lower the cost without losing performance. The second one is we can actually increase performance. And this is because many of the applications, the performance is actually bounded by the size of memory. And this example is with AI, machine learning. And by the way, you will go into more details on this as well. They have a problem they call data greater than memory problem. When the model and the embedding, the features can fit in the memory, everything is great. But once they out of memory, they need to go to the SSDs. The performance goes 1,000 times slower. It falls through a cliff once you because IOs now you're dealing with IOs. So now by delivering larger memory, we can solve this bigger, data greater than memory problem. They call DGM problem that we can solve with a big memory solution. And this is an example with a facial recognition inference. where the transaction per second can increase about 4 times, depending on the number of threads. X-axis is the number of threads, and the latency can be improved by 100 times as the speed it can recognize the face.
Charles, I see
Yes.
a couple of massive benefits, and one of them is the ability to not have to shard your database and break it up into multiple processes on multiple server levels.
Right.
But another one is to remove, let's say you had a large database that you could run on one large server.
Right.
You're removing the bus from that process, right?
Right.
The memory bus sits right next to the core processors.
Yeah.
And then you're removing all infrastructure between the processor and the disk as another boundary to processing speed. I think it's incredible.
Yes. I think once you put everything in memory, it's all through memory bus. You don't have to go to the PCIe. You don't go to the slower bus, and it's a big improvement. And the first thing you mentioned is also a great insight. Having a bigger memory. Now, for a database, I think for the people who are familiar with databases, one of the difficulties of databases is when you need to shard, and then when you need to do joins between those shards, and that slows things down a great deal. And now, if you have big enough memory, not only you can keep the database data into your memory cache, but if you can fit all of them onto a single server, you no longer need to incur this distributed join overhead, and that's gonna increase the speed of many queries as well. So that's another, I think, example that illustrating where a big memory solution can improve the performance that wasn't possible before. Yeah. Okay. So that's the sort of the big memory side. The third value proposition is from our snapshot, and I think that's where Nicole alluded to. This is with an in-memory database, and in this case, it's a Redis, 300 million keys, 315 gigabytes. So Redis, is a very good database, and it has actually a lot of built-in features as well, and it's very fast. So the orange bar is for this 315 gigabytes. The Redis have a way for you to save it. It has an RDB AOF way for you to sort of save it onto the storage system, so that you can restore from it anytime in the future, either after a crash or for any other reasons you want to restore to a previous image of that database. But it takes time because it incurs I/O, it does all these other stuff, serialization, deserialization, and all the other stuff. So it takes about 15 minutes to restore a 315 gigabytes Redis database. With our in-memory snapshot, now we are doing it right inside the memory. We don't need to move it around. And we restore the same database in about half a second. So it's a dramatic different experience once you have a memory that can remember, that you can save and restore right there from memory. It's 3 orders of magnitude in terms of a difference when you recover from the snapshot. And I think, Nicole, that's exactly what you described 3 slides ago. So this is a sort of the third value proposition is we, for the first time, make memory highly available. And then you can have many possibilities that can be built on top of this. And last but not least, that we believe, based on this snapshot, and combining that with cloud-native containers, Kubernetes, etc., that we are creating a feature. And now this is not available in 1.0. The previous 3, the numbers are all real. They are from customer POCs, and they were shipped in September. This is what we have on roadmap for 2021, is to create something we call a memory capsule. And memory capsule is allow us to capture a application state, especially those stateful applications in a container, and allow them to be moved around. So once now, for those of you who are familiar with cloud-native containers, Kubernetes, etc., these are awesome technologies. especially for stateless applications. Now, because those are ephemeral, you can kill them anytime, you deploy them anywhere, you kind of start them anywhere, it's all great. But the value prop kind of fell short as soon as storage is involved, as soon as the state is involved. You need to capture those state, and they then become messy and slow and heavy, etc. Now imagine all those states are captured now in memory. And then through our snapshot, we can basically put them into this memory capsule. And this capsule, now you can move them from server to server, from cloud to cloud. And this is a point in time in application that you can restore the application from that point in time, anytime, anywhere. And this basically provides a new system management paradigm how you can manage your applications in this multi-cloud world. And we believe there are many possibilities based on this. Once the persistent data are placed in memory, and once we have this snapshot mechanism and can capture it, and we are actively integrating it with leading Kubernetes-based mechanism to allow this whole process to work smoothly. So that's the sort of the 1, 2, 3, 4, the 4 value propositions that our product has, besides just the virtualization foundation itself, that we can lower the cost of memory, we can increase the performance of applications by the increased amount of memory, that we can, through our snapshot, can restore, capture and restore application much quicker, and we can providing a new paradigm of managing the mobility of applications. As I mentioned, I think this is a horizontal platform that can apply to all data centers, to all the clouds. And but we are startup, so we have to pick a few verticals to focus on first, that we see can enjoy the benefit the most immediately. And we picked 3 verticals to start first. So those are cloud service providers, movie studios who are making movies, and believe it or not, movies are now become bigger and bigger in terms of amount of data that need to be processed, and the financial services, both trading and consumer banks applications. And we're delivering various kind of some combination of the previous 4 value propositions I introduced. And here are some of the examples. With the cloud service provider, they are the one who are really interested in this TCO reduction. And this is not only the reduction of per gigabyte cost, like 30% per gigabyte cost, but with bigger memory, they can also increase the number of VMs per server. So increasing the VM density per server is another driver of cost savings for these cloud service providers. And for movie studios, they are most interested. They like the big memory stuff, which they can, right now they can only fit 17 seconds of a movie into their memory in a workstation for artists to work on. Now with bigger memory, they maybe can fit 1 minute of it into a workstation. So that's good. But what they like the most, and what their bosses like the most, is really the crash recovery case. So believe it or not, these artists are very creative, and they always find ways to crash their workstations. So on average, we're working with one of our POC studios. They average 1.2 hours of downtime per week per artist. So that's when machine goes down, and they need to recover it because everything in the memory is lost. They have to essentially spend work to recover. It takes hours for this machine to come back online. So there's a stats. There's like 7,000, 6,900,000 artists. So that's many hours of productivity lost. And it's not only that. Once the continuation of creativity is broken, it takes longer for you to get back into the zone. So by having a quicker recovery process by orders of magnitude, then you basically saves a lot of the productivity and the creative juice from these artists. And with financial services, they have a lot of in-memory databases. They use a lot of Redis. They use a lot of the time series database for trading and so on. And they have other sort of memory-centric applications that can benefit from this. But they are also the ones who told us this cost-saving aspect is the important aspect for them. Essentially, some of those customers have very large memory systems. And And DRAM is such a case, the bigger the size, the unit price actually go up. And also the server, server guys figure out ways to make margins. It's like larger memory system is where they make larger margins. So they spend majority of their budget on their server spending on memory. And by having a way of lowering the cost of that memory is also important to them. So here are just some examples of customers and the benefits that we bring to them. And here are a couple of the reference customers we have. We are very new. This is our first Tech Field Day. In some ways, this is kind of our party of sharing ourselves to the world. I mean, we had webinars before, but never have we exposed, like you will do, the inside of our product, like this session. And so we are very new. We're a brand new product, but we're lucky enough that we are working with about a couple dozen customers, and a few of them have become our paying customers. And here are just two examples who give us the permission to share. MEMX is a new stock exchange on Wall Street, and they obviously care about performance, and they care about fairness in terms of all their clients, all these banks on these exchanges are getting the same performance from the they get the ticker data all around at the same time within 1 microsecond of each other. So we are essentially using our big memory solution to enhance the memory-centric trading platform that they have, and this including allow them to share this ticker data quickly and fairly with all the subscribing banks. Intesa Sanpaolo is the largest consumer bank in Italy, and they have a lot of in-memory databases. In particular, the first one we supported is HaloCast, and we enable a clustered failover. It's a HaloCast cluster, and we can, our platform can allow that clustered database to recover easily using our snapshot mechanism. And Yue actually will go into that HaloCast use case in his section as well. So these are two real world examples of paying customers using our technology. And besides the customers, we are also working very closely with partners. Certainly, as you can imagine, Intel is a good partner of ours, and they're also one of the investors of ours, and we are essentially creating joint solutions with Intel, go to market to the customers, and there we are also working closely with certain software partners like HaloCast we described, like VMware. We are creating joint solutions with VMware as well, and kind of delivering solutions. And we are working closely with Red Hat, and not only with Linux but also with their OpenShift container platforms. But here I want to share a specific application. The significance of this is our product is software-only product. It's a subscription-based sort of SaaS model, software-only product that people subscribe. However, for the people who like to enjoy a system solution, we work with partners on this. And Penguin is our first partner. For those who are familiar with them, they make servers, but they don't only make servers. They make kind of solutions based on servers, and they are very well regarded in the market, the high performance computing market, and certain environments are demanding the performance. So it's a very good fit with our technology. And they just announced last month a solution called Live Data, and this is a big memory solution powered by MemVerge. And this is a hardware software solution together for those customers like to enjoy sort of a big memory server, all included from Penguin. So this is kind of going back to the future, to the vision we had 4 years ago, that we believe the future of infrastructure will be multi-cloud, will be memory-centric, and will be software composable. And we believe big memory software that we are creating is going to play a major role to bring that future to now. if you look at the data center on the left-hand side, this is what you have today. You have compute, you have memory, you have performance storage. These are often based on NAND flash and now or flash arrays that are powering your databases, powering your enterprise applications, and you have capacity storage that are mostly scale out, that are to handle the capacity of your bits, and they are interconnected by some kind of networking fabric. And this is a data center as of today, and altogether it's probably about $500 billion a year of spending. We believe the map will be redrawn. The compute will become more heterogeneous. There'll be new fabrics like CXL coming to market. The memory will become more heterogeneous, and we think it's going to become bigger. In fact, we think more and more applications will be run directly out of memory, and we believe the memory software layer to sort of harness these heterogeneity of memory and deliver them to the application will be a key enabling technology. And that is the technology that we are building with our memory machine product. And we think this is going to become a big market. This is going to become a $10 billion plus market, just like VMware. The server market that VMware pioneered 20 years ago become a $10 billion plus market. And we are a first mover, and we hope to be a leader in this space.